Welcome back. Let's talk all about covariance. So, hopefully, the example at the start of the lecture is connecting in terms of variance, because this is that concept applied across two measures, right? So, covariance is really, well, if we look here at this example, which is the number of adverts that a person's exposed to across time, and also the number of, say, packets like crisp packets that they buy. What you can see here, firstly, is that across these five people, is that you have differences between each person's number and the average number there. So for adverts, you have the average is 5.8, and for each of them, you can see some are exposed to more adverts than others. And then for packets, you see the average is around 11, and then some buy less packets and some buy more packets than others. So you can see that that's what's going on with each of the variables. But what's another thing you may notice is that when for someone, if they've been exposed to less than the average number of adverts, they get less packets of chips. And similarly, if they're exposed to a lot of adverts, they get more chips, right? So these variables, they actually co-vary, right, in their relationship. So the amount of, remember, the variance here is the error that you see, or the error within each of these compared to the average. And so what we're saying is that the sum of these deviances from the average are really varying in accordance to one another. So as one goes down, the other goes down. As one goes up, the other goes up. And so the covariance between the two variables is really the variance that they share. So we multiply the deviation for one variable by the deviations from another variable to get the cross product deviation. So what I mean by that is you calculate what this deviation is, and you multiply to get the cross product deviation, and you do that over and over for each person. That's why it's xi versus yi. And then this is the average for x and average for y. So here's the average for x, here's the average for y, and this is xi for the first person, xi for the second person. You do that for each of them. And that's how you get the cross product deviations. You then sum the cross product deviations and divide by degrees of freedom. Again, you can think of it as the number of people, so it'd be 5, but degrees of freedom, so it's actually 4, to get the covariance. And so this covariance, that's how you calculate covariance. So it's covariance is the sum of the cross product of here divided by the degrees of freedom, so it would be 4 here. And so that gives us a sense of the variance that's shared between these two variables. And so covariance reflects the direction of the relationship. So it's unstandardized. It depends on two variables having the same scale of measurement, right? And so for covariance to actually to work, it needs to have the same measure. So what are some problems with covariance? Well, it's not a standardized measure. The size depends completely on the units of those measures. So sometimes you could have a covariance that's very high, others that are very low, and it's really just dependent on the unit of measure there. So you can't really compare the covariance between two measures here and the covariance of these other measures here in an objective way. So nor could you say whether the covariance is particularly large or small just based off of whatever that number is, unless both those data sets are of the same unit of measure, then you can compare them. But if they're different units of measure and you calculate the covariance, then you're not able to get that sense. So how do we address this? This is a pretty important problem. It gives us a good sense of the direction of relationships between variables, but we aren't able to really compare between variables because they're in different measures and different scales. So what we do is we standardize. So that's how we overcome the problem. And to standardize, that allows us to get the correlation, which is a measure of the standardized covariance. So you get the covariance and you divide it by the product of the standard deviations for each of the variables. So the relationship between x and y is the covariance of x and y divided by the product of the standard deviations of x and y. So hopefully you can see now all the threads of, we start from variance, we go to with one measure to understand that about the errors and how you sum them up and how you get the overall variance, and then from there how you look at covariance as when they're in the same measure, and then from there we can get from covariance to getting a standardized measure like a correlation coefficient, which is you divide by the standard deviations of both x and y. So what's the difference between covariance and correlation? So the size of covariance depends on the measurement scale used. If the variable use different scales, you can't compare them. For example, if you do covariances of heights of two different people, like men and women, and then the weights of men and women, then you wouldn't be able to compare them at all. But when you standardize the covariance, so you divide them by the cross product of the standard deviations, you get a correlation. And you can compare. Maybe the correlation of heights is 0.7 and weight is 0.6. So correlation it's an effect size. It's a standardized measure of strength of the relationship. So I could say in that example, the effect size here is larger than the effect size here, even though the measures are on different scales. So it's really a powerful tool to allow us to compare between different measures. So hopefully that makes sense. If not, these questions are going to be a good test as to whether or not it does make sense to you. So the covariance between x and y is 1.2. The standard deviation of x is 2, and the standard deviation of y is 3. The correlation is what? And I've put the formula here for you to give you a bit of a sense. So pause the video, have a crack, and hopefully you've started the video now and you're looking at this and you're saying, well, the covariance is 1.2, standard deviation of x is 2, y is 3, so 3 times 2 is 6. So it's 1.2 over 6, which should give us 0.2. So that's what we see there. And I've done the maths for you there as well, so as a bit of a helping hand. So excellent, so that's good to see. The next one is the covariance between x and y is 5, standard deviation is 2, and the standard deviation is 4 for y, and 2 for x. So 4 times 2 is 8 on the bottom, in the bottom of that formula. On the top of the formula, you have the covariance as 5. So 5 divided by 8 gives you, 8 goes into 5 6 times, yeah, so it'll be 0.63. All right, excellent. So this is the correlation. So we've gotten the correlation. So now we can see, we can actually, once you have the correlations, you can compare these two. So you can say this is 0.2, this is 0.63, so this correlation is larger than the other one, or the size of the effect is larger. So how do we interpret correlations? Well, we can use the coefficient of determination, which is the proportion of variance in one variable that can be accounted for by another variable. And I mentioned that earlier in our example when we were looking at the model and we are seeing what that r squared value was. So for example, if the correlation is 0.6, then r squared is 0.36. So that means 36 of the variance is shared between these variables, right? So that's the key takeaway there. To calculate how much of the variance is shared between variables, you calculate the coefficient of determination. Excellent. So a correlation is simply an effect size. The question you may now have is, okay, say I have a correlation of 0.7 or a correlation of 0.2 or a correlation of 0.5. I know how big they are relative to one another, but what about in terms of absolute strength? Well, there are some guidelines that were developed. Cohen provided some guidelines to determine the strength of correlation and suggested that weak correlations are between 0.1 to 0.3. Moderate correlations are 0.3 to 0.5, and strong correlations are greater than 0.5. So that's an example of how you could, and then here it is for r squared as well. So that's a guideline that people can use, and it's highly cited, these guidelines, but they are just guidelines, right? I think what's important as well is understanding the strength and the context of the area. Or so you may have an effect which is termed as weak here, 0.3, but maybe the typically effects are really small in the area that you're looking at, like many population level studies. And so sometimes if you see 0.3, that could be massive in a relative sense. So these are just guidelines. They've been around for a long time, but they also are not they're not what you should be always using as your justification. These guidelines are great and they can form part of it. The other part and really important part is where does this correlation or effect size sit in the context of this area of research? And so that goes back to the example I gave you earlier in terms of that numeric memory scale and the size of the effect in relation to the scale. These are different ways we can think of in terms of effect sizes. So here's the size of correlation. Here's a 0.55 correlation that I've generated with some fake data, and p-value is less than 0.05. What's the percentage of shared variance? Was 30%, right? So square root of 0.55 should give you that 30%. And here you have a weak correlation, which is negative 0.2. Statistically significant. What's the percentage of shared variance between these two variables, x and y? It's 4%. So 4% of the variance is shared, whereas here it's 30% of the variance is shared. Here's another example of a moderate correlation, which is 0.41. Now, how I'm judging all of these sizes is based off of this table, Cohen's effect sizes, weak, moderate, and strong. So the moderate correlation is 0.41, p-value is less than 0.05, so what's the percentage of shared variance here? It's 17%, right? And so that's how you can get a sense of correlation to your sense of shared variance between the two. Now again, just emphasizing that shared variance is the coefficient determination. That's where you square your correlation and you get your coefficient determination. Excellent. Now, as I said, there's other interpretations as well. Those Cohen guidelines are one. Evans guidelines are another for interpreting strength of correlations, and it breaks it down further into very weak, weak, moderate, strong, very strong. There's different guidelines available. I just want to make you aware of these two, which are widely used. But again, keep it in mind within the context of your area that you're investigating in research. Okay, excellent. So what we're going to do now is we're going to look at assumptions and limitations of using Pearson product moment linear correlation. So here are sort of the list of assumptions that we need to consider, and also limitations when it comes to using Pearson's product moment correlation. We have to ask ourselves, what are the levels of measurement? The normality of the data, is it linear related? The effects of outliers, nonlinearity, homoscedasticity, no range restriction, homogeneous samples, correlations, not causation, and dealing with multiple correlations. So we'll cover all of this right now. So let's start with normality. So assumptions that you have sampled from populations with normal distribution of your residuals, but can start by looking at individual variables. So what I mean by this is, so to run something like Pearson's correlation, your residuals need to be normally distributed. Many people actually think that this assumption of normality relates to your individual variable. And if you have a variable that's skewed in your analyses, then you can't do correlation. Well, in fact, you need to run the analyses and check your residuals and see if they're normally distributed. So this assumption relates to the residuals, not the variables. But the reason why that misconception is permeated in statistics is because if you have non-normal residuals and one of your variables is not normally distributed, it's likely that that variable is the problem. And if you're to address that through, say, a log transformation to make it more normally distributed, then your residuals could be normally distributed as a result. But this assumption relates to the residuals, not the variables. But there's a relationship between them that's nuanced. So you want to avoid relying on only one indicator of normality. So you want to actually use histograms and skewness and kurtosis statistics when assessing normality. Really, I look a lot at figures and histograms when looking at normality, typically because it's a good sense of it. You get a good visual sense, but also the skewness and kurtosis statistics, they can sometimes be misleading in very large sample sizes. So they can say that it's non-normal when in fact it likely is. So you have to consider it in the context of the data that you're looking at as well. So that's normal. So assumptions that for normality is an assumption you have to meet to say that it's sampled from populations with normal distributions, and you can look at your individual variables there. We have to assess the effects of outliers, so they can disproportionately increase or decrease your correlation coefficient. If you have an outlier, it can completely change your correlation depending on how influential it is as well. So how do you deal with this? You compute R, with and without outliers to see the effect. If you've identified outliers, you say, well, okay, how does this correlation change when I remove the outliers? And how does the correlation change when you have them in there, and see what the difference is? If there's not much of a change, then you could say, well, there's not much of a difference with the outliers, and so you include them to increase the overall power of your analysis. You can get more data for outlying values. And also with the outliers, you always have to ask yourself, why are these outliers here? Do they represent the sample population of interest in this study, or are they in fact perhaps a separate population sample that is not intended to be included in the study? You can recode outliers as having more conservative scores as well, and there's literature around how to do that. You can do a transformation of your data as well, and you can also recode the variable into a lower level of measurement using a non-parametric approach. So rather than doing a Pearson's correlation, you can recode and change it into ordinal by ordinal, do Kendall's, or nominal by nominal, and do a chi-square test if you wish. So those are ways in which you can address the effect of outliers. But typically, most commonly that I see is, each of these approaches have merit in different situations and circumstances, which is why I want to highlight them all. But often you compute the correlation with and without the outliers to see whether there's differences, or really to quantify what the influence is of those outliers. So if there's a nonlinear relationship, this is where you need to check your scatter plot. And this is where statistics are useful in themselves, but they can, you always have to sort of, wherever you can, try to visualize what you're modeling, because many times things like this may occur where you have this line that you fit. If you just plug these two measures in, x and y, and you run a correlation, you have a negative 0.4 correlation. You may not be thinking any more of it, but this is why doing descriptives is important, because you'll see actually the lion's share of this variance is captured by a nonlinear line rather than this linear line in red. So it's important to always graph your data to see what's there. So what do you do if your data is nonlinear? You use a nonlinear mathematical function to describe the relationship between the variables. So it's best to keep it nonlinear and use that nonlinear. Maybe a quadratic function is something you'd be looking into. Or you could, some people transform variables to create linear relationships. So you can log transform often, which can either condense the data or spread it out and allows it to become more normally distributed. So that's another way in which it can be addressed, but often it's fine if it's nonlinear, and it's better to make sure that the statistics and approach that you use maps onto the data that you see. So that is what you need to do there. Skedasticity is a concept. There's homoskedasticity and heteroskedasticity. So homoskedasticity is where you have an even spread of observations around the line of best fit. Heteroskedasticity is where you have an uneven spread of observations around the line of best fit. So it can be assessed visually by using Levene's test. It can be assessed visually by plotting, and statistically by using Levene's test. So you want your data to typically be homoskedastic for correlations and linear regression models, which simple correlation is. Now, here are some examples of taken from Andy Field's textbook that shows when you plot the standardized residuals by the predicted values, you see that in the top left you have what you would expect in a homoskedastic distribution or spread of data points. You see that they're evenly spread across that line, right? Because it's an even spread around of observations around the line of best fit, which is what we see here. Now, this is great, and this is what we're looking for in the top left. Now, if you have this sort of funneling that's occurring with your data, that's where it's heteroskedastic. If you see this sort of shape occur here, that's where it's nonlinear. And then if you have this funneling and a typical shape here, that's where you can say it's heteroskedastic and nonlinear. So each of these three cases poses a potential barrier to conducting Pearson's correlation coefficient. So you need the assumption of homoskedasticity to be met in order to run the analysis. So you need to check this plot when you're doing it. And so another example is range restriction, which occurs when the sample has a restricted or truncated range of scores. For example, the age in a student sample, many participants are in the 18 to 20 age bracket when university studies are done. And so if the range is restricted, you can do your analyses, but you have to be really cautious about generalizing beyond the range for which data is available. So income may not continue to increase linearly with age. And so if you're extrapolating from that data, this takeaway is that you shouldn't be. You should really be focusing on modeling within the data that you have and being very careful about the interpretations you make, because the model will just plot a line through your data points and even go beyond where possible. And so if you don't consider that within, well, what does my data actually look like, then you may make incorrect inferences or inferences that aren't based in data that you have. So that is the key thing to take away there with range restriction. So, and here's examples of the same data with different ranges, right? So you may look at your data that you've collected in people from 0 to 20 years of age, and you're looking at some measure, and you see actually, yes, linearly related, and you may incorrectly infer that across the lifespan this is linear, but in fact, when you take it across the lifespan, you see actually it's nonlinear, and it's quite clearly nonlinear. So range restriction, you need to be cautious about what that means within the context of your data, and keep your interpretations focused within your data. And this applies when you're critically analyzing studies as well. If a study is conducted in people of a certain area, like in Australia, or if it's of a certain age range of people, then the conclusions need to really be tempered within the context of what the data shows. And so if they're extrapolating from that, then that generalizability needs to actually be supported by evidence from other studies that actually support that as well, not just if they're extrapolating from their own study, then that generalizability may not be founded as well. So important to keep that in mind. Heterogeneous sample, this is where if there are different subsamples in your data, it can artificially increase or decrease the overall correlation. And you can calculate R separately for subsamples, and as well as overall then look at the difference. So this essentially means within your data, if you think you can identify different samples of data, then you may find that the correlation can change. So your overall correlation may be 0.7, and it's all positive. But then what you find is when you have, you may have 4 groups within that, and if you map them, they all show this effect. But in fact, the individual groups are in the opposite way in terms of their correlation. So really considering your sample, is the sample one sample, or are there subsamples, and do the correlations hold in that subsample? And what I've just described there is Simpson's paradox. So where you have a subgroup that when you look at the individual relationships, it's actually in the complete opposite direction. So a relationship observed in the aggregated data can reverse when a third variable is considered. So here's one where you have study time and test scores, and you could, if you just looked at those 2 variables, you'd see actually the overall effect decreases across them. But then if you don't consider the effect of school on here, so there's 2 schools that are there, then you'd see actually within schools we see an increase in trend, that the more people study, the better their test scores, which aligns with what we think. So this is where it's important to consider the impact of individual groups. And I think I pointed this when emphasizing the importance of correlation at the very start of this lecture, but it does not equal causation. Remember that just because 2 variables are related, this does not mean that one causes the other. And inherently humans like to think in causal ways, because it's how we operate and how we navigate the world. A classic example here is shark attacks increase with more ice cream sales. Here, the example shows that there's a third variable that confounds this relationship, which is that Ice cream sales happen more in summer. People swim in the water more in summer, so that's where you may have an increase in shark attacks as a function. But if you were to causally interpret this correlation as is without that, thinking of the alternative explanation, you would just say, oh, eating ice cream causes shark attacks. And it seems absurd, but there's many examples where it's not as absurd and these causal interpretations are made. So yeah, the alternative explanation is people eat more ice cream when it's hotter, and they're more likely to tend to swim more. So with more people in the water, shark attacks become more likely. So here is a great example. If you click on here, it gives you a whole bunch of spurious correlations. So they're just correlations that appear in nature, and shark attacks and ice creams are one of them. But there's a whole host of examples that are posted on this website. So I encourage you to have a look at those examples to get a sense of it. Now, why is this such an important topic? Well, because when two variables are causally related, they are highly correlated, right? But how do we tease apart that nuance of causation and correlation? Well, in part, we do that by research design. So we can do randomized control trials and try to mitigate the effect of confounds and try to determine actually the effects we see are because of the drug or the intervention that we've provided to these groups. But it's an important nuance to consider when thinking of correlation. So the back of your mind, always keep in mind that correlation does not mean causation, but it's important to consider, well, if we were to think about what is the justification for these measures to be causally related to one another, and what evidence would we need to see for it to be causally related? Could it be related to factor X, Y, Z, and can we adjust for that in a multiple linear regression model to address this? So that's another key takeaway. So how do you deal with several correlations? Well, you can do a scatter plot matrix, which organizes scatter plots and correlations amongst several variables at once. It's a really nice way of visualizing all your data and their relationships to one another. And so I've generated it here using the CARS dataset in R. And so what you see here is the scatter plot matrix, where you have all the different, these are the different variables that you have, and it shows you their relationship to one another in scatter plot. And their distributions, and it also plots their correlations. But if you just wanted their correlations table, you could see it here. So MPG, I think this is weight that's there of these cars, and it shows you the relationship between them. So of course, the relationship between a variable and itself is perfectly correlated. So it's 1, so that's 1 across there along that diagonal. And then weight and MPG is negative 0.87. And then here, weight and MPG is 0.87. So sometimes you may see correlation tables reported with these ones in empty, because they're sort of the exact same, because you see multiple connections between these measures. But ultimately, what I want you to take away here is that this gives you a sense of, you're looking at your measures, you run a correlation table, and you get a sense of their relationship to one another. So that is the key things, the key assumptions that you need for doing correlations, but also strengths and limitations and things to think about. So what are the key summary? Well, covariation is everywhere, and things vary between one another and vary together. And correlation is a standardized measure of covariance, the extent to which two variables correlate. It ranges from -1 to +1, with more extreme values indicating stronger relationships. So if it's 0.9 or -0.9, they're indicating stronger relationships versus 0.2 or -0.2. And correlation does not prove causation. That's the key takeaway, which I'm sure you may already be familiar with. But it's important to not just leave it at that and say, well, we can't causally conclude anything. Actually, we need to have courage as researchers to use more than just the correlation, but our justification as to why we think variables are related to one another. So this is where nuance, we use different designs like randomized controlled trials to give strength of evidence to it. But certainly alone, just looking at a correlation, you wouldn't infer causation from it alone, but you take all the evidence together to make an inference through that. What's the purpose of correlation? Hopefully this is clear to you now, which is the relationship, association, shared variance, or co-relationship between two variables. And it gives you that standardized measure. So you can measure the effect size of two variables here and two variables here on different scales. You can compare those effect sizes. And then it depends on the level of measurement. So whether it's nominal by nominal, ordinal by ordinal, or interval ratio by interval ratio, or interval ratio by nominal, that determines the type of correlation you'll be doing. And again, there's really four key categories here, and then in many of the others, you can recode down the levels to do the other types of analyses that are there. So what are the steps to take? Well, the first step, you have to identify the level of measurement of your variables. Is it nominal, ordinal, interval, or ratio? And this will help guide the type of correlation and graph to use. And check your graphs for these key components, such as linearity, outliers, stochasticity, range restriction, and subsamples to consider. So those are the key things to take away. You want to consider effect sizes. So how big is your effect size? So you look at phi or Cramer's V, your correlation coefficient or your coefficient of determination. Look at the direction of the relationship. Is it positive? Is it negative? And the significance from the p-value, statistical significance. And remembering that statistical significance alone doesn't show you that it's clinically significant or meaningful. We have to take into account the effect size to understand that more. And you can interpret and discuss your findings and relate it back to your hypothesis. What are the limitations? And based on heterogeneity, range restriction for making more causal inferences. So in interpreting correlations, we have our guidelines here. So weak, moderate, strong with Cohen's guidelines. And we talked about the assumptions and limitations for Pearson's product moment linear correlations, which are all of these factors. So next week, we're going to look at exploratory factor analyses, so including an introduction to factor analyses, exploratory factor analysis examples, and steps to run your own exploratory factor analysis. But that's everything to do with correlations. Hopefully, you walk away with a sense of not only understanding correlations, but seeing that they're everywhere. They're very, very important, and they form the foundation of how we operate with the world around us, and we should do that carefully and in a considered manner. So in saying that, that's it for today. Have a lovely day, lovely week. I'll see you guys in the next video.